Hello everyone, this is Cube in a Group episode 5 and today we are going to look at the subgroups. You may think of another word, subset, when you first see this title, and I will translate this concept in this video again by using the Rubik's Cube. This video is an introduction to familiar ourselves with the language of subgroups so that we can better understand the Lagrange theorem in the following videos. Before we start, I remember that we have some questions left in the last video. So first I will review some basic concepts of the parity of permutation. As we've learned, an odd permutation is the product of an odd number of transpositions, and an even permutation is the product of an even number of transpositions. So the first question is, how many permutations are odd, and how many of them are even? If you've tried some examples on your own, not just in the cube group, but also, for example, in the permutation group of just 4 elements, you will discover that the number of odd and even permutations are equal. And to prove this, we can consider mapping each even permutation onto an odd permutation, namely by considering the map Q to QP given as follows, and prove that it is a bijection. For those who are unfamiliar with this term, a bijection means that a map is both injective and surjective, and it implies that the image and the pre-image are of the same size and have a one-to-one correspondence. The second question is, do all odd or even permutations form a group structure? For the odd permutations, the answer is no, because we've proved that the identity is an even permutation, and therefore it doesn't belong to the set of all odd permutations. But for the even permutations, you can check by the group axioms in our first videos that the answer is yes. These two properties give a very interesting conclusion. If we delete all the odd permutations in a group, which is exactly half of the group, the remaining cube group is still a group. Actually, this group that contains all even permutations in a finite set has a special name, which is the alternating group, and is denoted by A sub n. Now, if we denote the permutation group over the set 1, 2, 3 all the way down to n to be S sub n, then we find A sub n is a subset of S sub n. But we've already confirmed that both A sub n and S sub n are groups. The reason why I want to introduce the alternating groups here is to visualize how one group contains the other group, of course, under the same operation defined on a bigger group. Therefore, mathematicians think of a way to define this relationship by introducing subgroups. Given that G is a group, then a subset H of G is called a subgroup of G if H also forms a group under the operation of G, denoted by H is smaller or equal to G. And for example, we know that a group generated by a basic operation R is a subgroup, because by doing R for 4 times, we come back to the identity and the other group axioms still hold. Some more complicated subgroups may look like this. If we do a series of actions RU R prime U prime on a cube and denote this as P, then by doing P for 6 times, we also come back to the identity. Actually, you may discover that you can repeat any sequences of actions on a cube for many times, and finally it will come back to the identity, and by doing this you get a subgroup. But why subgroups are so useful is because that the description of subgroup is a foundation to the Lagrange theorem, which claims that the size of any subgroup H of G must be a divisor of the size G which contains H. This actually helps us calculate the number of times we must repeat a series of operations to go back to the identity, not only on the cube but also in real mathematics. But before that, we have one question left to solve. What is the size of G? We have already gone through a long way here after we studied the permutations and groups, and I think we are able to solve this question quite soon. Here, the G is the cube group, and the size of G is the number of total variations on a cube group. The answer is embedded in this formula. For the numerator, you can link the formula to the number of edge cubies and the corner cubies. But for the denominator, you should carefully think about why we divide these numbers out. I will sketch a proof for the formula in the next video, which is also the number of total variations of a cube, and hopefully we can come to the Lagrange theorem soon. If you liked the video, please feel free to subscribe to my channel or comment your questions below, and see you next time.